Mark, whenever you're ready, just feel free to get started there.
Hobson said these two further things. The one was, he said that if you look at this random mental activity that's generated in the way I've just described, you can find meaning in it in the same way as you can find meaning in an ink blot. The ink blot itself is meaningless. It's just a random outcome of how the ink fell when you fold the page on which the ink blot has landed. It creates this meaningless pattern, but you can find meaning in it. You can say, it reminds me of a butterfly, or it reminds me of a bat, or a vampire. And this might say something about you, the meaning that you find in the ink blot. But the crucial thing is that the meaning isn't actually in the ink blot. You have projected it onto the ink blot. It comes after the fact. And so says Hobson, dreams are inherently meaningless things, just like ink blots are inherently meaningless things. And psychoanalysts project meanings onto them in exactly the way that worried Popper, that you can do anything you like if the method that you use is finding meaning behind things, rather than the kinds of methods that Hobson and Jouvet and Iserinsky and Kleitman and Dement used, where there are objective ways of testing your theories and verifying by falsifiable predictions whether you're on the right track or not. So this was one of the things that Hobson said. The other thing that Hobson said was, as I've told you, therefore the Freudian theory must be wrong. The dreams do not work the way that Freud said. There are no wishes, there are no motivations, there's no psychodynamics, there's no inherent mental process behind the dreams at all. And so Hobson presented these findings to a meeting of the American Psychiatric Association in 1976. And after the lecture, a vote was taken as to whether or not Freudian dream theory was scientifically viable anymore. And that vote went 2-1 against Freud. This was a momentous occasion, bearing in mind how influential psychoanalysis had been in American psychiatry. For the assembled membership of that American Psychiatric Association to concede that the Freudian dream was not scientifically tenable anymore brought us back to the idea that the popular notions of dreams being meaningful, there being some hidden message embedded in them from the other side, etc., etc., even in its sort of biologized version that Freud came up with, where saying that the other side is in fact the unconscious mind, that the message is really a message from your own inner world rather than from some metaphysical dimension, etc. That all of this was just bunk. That dreams were meaningless, inherently meaningless, random activation of the cortex by the firing of these cholinergic neurons in the pons. Activation followed by synthesis. I began a study which I'm now going to report to you. I wasn't especially interested in Freudian dream theory. It had been debunked. I was a neuropsychologist, and what I was interested in was the synthesis side, the cortical side of Hobson's theory. I predicted that if what the cortex is doing is joining the dots, the randomly activated dots, as it were, in the cortex, then damage to different parts of the cortex should have differential effects on the content of dreams. Damage to the visual cortex might result in non-visual dreams, I predicted. Damage to the somatosensory cortex, which leads to hemianesthesia and hemiplegia, paralysis of one side of the body, should have us moving in our dreams with only one half of our bodies. Damage to the language cortex should result in non-verbal dreams, and so on. All of these predictions, I want to tell you, were disconfirmed. None of that happens. It was a great surprise to me. The only one of my predictions which was in fact confirmed, I predicted that the prefrontal cortex, this part of the brain, which sets human beings apart from chimpanzees and other primates, we have very highly developed prefrontal cortex. This part of the brain is in charge, as it were. It's the executive control center of the mind. Since we do not seem to be in charge of what happens in our dreams, I predicted that damage here would have no effect on dreams. I predicted that this part of the brain does not participate in dreaming, and that proves to be correct. Damage to this part of the brain has no effect on dreams. Blind raters, that is to say, people who do not know whether they're looking at the dreams of a patient with no frontal lobes or the dreams of you and me, they are unable to distinguish the dreams from each other. That was the one and only of my predictions that was confirmed in this study that I began in 1985 and ended 10 years later. It took me 10 years to do the study because I wasn't studying rats and cats. I was studying human beings because I needed dream reports. I needed to see how the content of dreams was altered by damage to different parts of the brain. So this slide here, the dark blue area, corresponds to the area of the brain that we're talking about, the prefrontal cortex. Damage here has no effect on dreams. But what I found, the other things I found were really equally interesting, if not a lot more so. And these other findings were surprises. The first surprise is indicated by this light blue area in the top left image on the screen. This is the mesopontine tegmentum. This is the part of the brain that is responsible for generating REM sleep, the part of the brain that Groote and even more precisely Hobson had identified as the dream generator. It's here, this area here. Now, what I found was that damage here, although it does lead to a loss of REM sleep in human beings, just as it does in rats and cats, it does not lead to a loss of dreaming. That these patients, I had 18 of them with damage in this part of the brain. By the way, I studied 361 patients. 18 of them had damage here, and they all reported ongoing dreams. And even if you wake these patients up during the middle of the night, you get no dream, you get no REM, but you do get dream reports. So this was a really shocking surprise because the ABCs of behavioral neuroscience state that if a part of the brain is responsible for a particular mental function, then loss of that part of the brain should lead to a loss of that mental function. But what I found was it applies to REM sleep. You have a loss of REM sleep, but you do not have a loss of dreams. That means on the ABCs that I spoke of, that this part of the brain cannot be the part that's responsible for dreaming, that there is in fact a dissociation between REM sleep and dreams, that although REM sleep is lost with damage here in all species, we can determine in human beings that dreaming is not lost. This suggests that dreaming and REM sleep are not the same thing. This was even more strongly confirmed by virtue of the fact that I found that damage here in what's called the parieto-occipital junction, this area of the brain, that damage here to this part of the brain which is responsible for mental imagery, that damage here leads to a loss of dreaming, which is not surprising because if you can't generate a mental image, how can you generate a dream? But these patients continue to have REM sleep. That's what we call a double dissociation of function. In other words, damage here leads to a loss of REM sleep with a preservation of dreaming, and damage here to these brown areas leads to a loss of dreaming but preservation of REM sleep. So dreaming and REM sleep were doubly dissociable. Even more interesting, and this is the last of the several findings that I made, but I won't report them all, it was that damage in this area marked in red. Red means important. Damage to this part of the brain, which I'll show you on this slide. It's the white matter underneath the cortex here on both sides. Damage deep inside of the forebrain, underneath the cortex over here on both sides. This too leads to a loss of dreaming with preservation of REM sleep. So my main focus after that finding was, what is this part of the brain doing? This part marked in red, because clearly this is crucial for dreaming. Unlike the brown area where there's no surprise, if you can't generate mental imagery, you can't generate dreams. It wasn't clear at all why damage here should lead to a loss of dreaming. It wasn't clear what this part of the brain is doing that's so important for dreaming, because it is clearly doing something really important for dreaming, something essential for dreaming, because damage here leads to a loss of dreams. Here's a rough and ready slide, a facsimile of the damage in my patients, the actual 9 patients I had with damage over here, all reported loss of dreams, and it was possible to show that they continued to have REM sleep. And if I woke them up from REM sleep, I got no dream reports. I had only 9 patients here, which is not enough to be completely sure that what you found so unexpectedly can be used as a basis for coming to the really surprising conclusion that dreaming and REM sleep are 2 different functions. But when I looked at this slide, I looked at this overlay of the damage in my 9 patients, I was reminded of the fact that this part of the brain was in fact deliberately targeted by psychosurgeons in the 1930s and 1940s when they performed an operation called prefrontal leucotomy. They severed the fibers in that part of the brain for the treatment of psychosis. It was found that if you cut those fibers, then psychotic patients improve in the sense that they no longer suffer hallucinations and delusions. And I went back to the old reports of the mental effects of this operation. And what I found in hundreds of cases reported by Jerome Frank in America, by Partridge in England, by Schindler in Germany, was that cutting these fibers in these psychotic patients led not only to a loss of hallucinations and delusions, but also to 2 other things. One was that the patients were no longer motivated. They lost their volitional oomph. They lost their motivational drive. They were described as adynamic, akinetic, abulic, amotivational, aspontaneous. But in addition, what was observed was, thirdly, that they no longer dreamt. And Schindler went so far as to say that if after the operation the patient continues to dream, this is a poor prognostic sign. It means the operation hasn't worked. And that made sense to me, because I thought, well, if you're able to generate a dream, which is after all a delusional and hallucinatory state, then you're still able to generate hallucinations and delusions, the very thing that the operation was meant to prevent. And so Schindler's observation that this is a bad prognostic sign made sense to me in light of my findings that these patients with damage here, my findings, which in fact turned out not to be original, because the old psychosurgeons had found the same thing. Damage here leads to a loss of dreaming. And now the operation prefrontal leucotomy was abandoned in the 1950s, not for ethical reasons, interestingly enough, but rather because a new treatment for psychosis became available in the form of antipsychotic drugs. And antipsychotic drugs, very interestingly, act on a pathway, block activity in a pathway that courses through exactly this area. Here is that pathway. It's called the mesocortical mesolimbic dopamine system. Now, remember, I told you that the part of the brain over here that generates REM sleep, it releases a neurotransmitter called acetylcholine, which activates the forebrain. But the part of the brain that we're talking about here is not cholinergic, but rather dopaminergic. The neurotransmitter of interest in this circuit is dopamine. And antipsychotic medications still to this day block activity in this pathway by blocking dopamine. They are dopamine blockers. So that led me to the hypothesis that this is the circuit that generates dreams, rather than the circuit that generates REM sleep. I then proceeded to test that hypothesis by means of the experimental method that Popper says we must use. In other words, I generated falsifiable predictions. I said that if we take normal subjects and we give them antipsychotic drugs, in other words, we block dopamine in this circuit, they should have fewer dreams. And if we boost dopamine in that circuit by giving levodopa, dopamine boosters, then the research participants should report increased dreams. And that's exactly what I found. And a colleague of mine, Ernst Hartmann, found the same thing, that if you give research participants dopamine, they have more dreams, more emotionally intense dreams, they have longer dreams, they have more bizarre dreams, and they have more nightmares. In fact, everything about dreamness that we measured was increased by dopamine. And conversely, dopamine blockade led to less frequent dreams, shorter dreams, less emotionally intense dreams, less bizarre dreams, and fewer nightmares. So the predictions were confirmed. By the way, the alternative prediction arising from the cholinergic hypothesis was disconfirmed. In fact, if you block acetylcholine with a drug called scopolamine, which is a anticholinergic, on Hobson's theory, this should lead to a loss of dreams or a reduction in dreams, but it does the opposite. These patients not only continue to dream, these research participants, they in fact report more dreams. They even dream during the day, in the sense that they hallucinate during waking life. So this is the value of Popperian science, of falsifiable predictions. You can compare one theory to another, and you can confirm one and disconfirm another. But this is only one method. The method of pharmacological manipulation. There are other methods that were applied too. In fact, I shouldn't say it's only one method. I've so far reported two methods. The one is that severing these fibers, in other words, the lesion method, damaging these fibers leads to a loss of dreams. And the chemical method, blockading those fibers, leads to a reduction in dreams. My colleague Alan Brown then used this method called positron emission tomography, where you image which parts of the brain are activated in a particular mental state. The middle row here is during dreaming sleep, REM sleep, remember, which is when 90% of dreams occur. What he showed, interestingly, as I found with the lesion method, I showed that damage to the prefrontal cortex has no effect on dreams. Brown found that the prefrontal cortex is not activated during dreams. In fact, he shows here, this is the part of the brain that deactivates as you fall asleep, the frontal lobes. And when it reactivates during REM sleep, this part of the brain does not reactivate. So this is consistent with what I found, but also consistent with what I found is that what activates most intensely on positron emission tomography during dreaming sleep is the mesocortical mesolimbic dopamine system. There it is, switched on like a Christmas tree. And this is very interesting. This clearly is the part of the brain that is most active as we enter dreaming sleep. Interestingly, what also activates is this area here, which is where my patients had damage. My patients who had damage here in the parieto-occipital junction, the part of the brain that generates mental imagery, I showed that damage here leads to a loss of dreaming. And Brown's study showed that not only is the dopamine system activated very intensely during dreams, but also there's an activation of these perceptual cortices the parieto-occipital region during dreaming sleep. So this confirmed the pharmacological and lesion findings that this is the area that is most intensely involved in the generating of dreams. The two further studies, these two studies here, used two other methods. Dahan showed that by recording from single cells, he showed that these dopamine neurons fire at maximal rates during REM sleep. And Lehner found, using another method whereby she measured the amount of dopamine that's released, it's called microdialysis. She showed that dopamine release is maximal during dreaming sleep. So now we have lesion evidence that shows that damage to this pathway leads to loss of dreaming. We have pharmacological evidence that chemical boosting of this pathway leads to increased dreaming. Single cell recordings of the neurons at the origin of this pathway showed they fire maximally during dreaming sleep, and measuring the release of dopamine at their terminals shows that dopamine is released maximally during dreaming sleep. So all of these 5 different lines of evidence led us to conclude that this is indeed the part of the brain that generates dreams.
Thank you for listening, and I hope you enjoyed the show. If you'd like to hear the full version, you can do so with the Weekend University Premium membership. This gets you access to our master library of over 230 talks and interviews with the world's leading psychologists, professors, and authors, as well as transcripts, CPD certification, quizzes, and unlimited access to the recordings from our annual conferences. For more information, please go to theweekenduniversity.com/membership.